So as satellite traffic moves from geostationary satellites to low Earth orbit or LEO satellites, massively more bandwidth is available to each user. This does not necessarily mean that the quality of experience will be perfect on LEO satellites, and I'll try to explain why. Imagine two users that are using low Earth orbit satellites for internet connectivity. LEO satellites, well, there's a lot of them, and they circulate around the Earth, giving available internet to the users. In this case, let's assume that one satellite up here is serving both user 1 and 2. Satellites have a concept of beams. So on the satellite, there'll be several beams. Let's imagine that one beam is pointing something like this. For user 1, he's comfortably within the beam and getting a good signal, a good throughput. User 2 is just on the edge of a beam and will have poor signal before the next satellite picks him up and puts him in good signal conditions instead. So what we will see, if you imagine something like this, where you have capacity, is really a function of the signal on the y-axis. Let's say that at best you're going to see 250 megabits per second. But as the satellites move across the sky, which they do pretty quickly, you will get a drop in bandwidth in an oscillating way like this. And for upstream, it will be more like no more than 30 megabits. Same oscillation. Of course, you're not using all of your bandwidth all the time. So on the secondary y-axis, let's just call it utilization. So utilization maybe goes like something like an inverse of the capacity curve. And up here is the 100% curve. So on the downstream, my user here in my example is not hitting 100%. On upstream, let's do the same thing. Utilization as a percentage. And when the utilization here on the upstream hits 100%, of course it can't go higher than that, it will flatline and then come down again. Now what happens here during this phase is nothing good. If you imagine how many packets are queued because they cannot be transmitted, let's call this queue length in milliseconds. No queuing happens on the downstream. And on the upstream, there will be nothing, 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 nothing. And then longer, longer, longer queue. And then it will quite quickly drop off again like this. So this triangle here is a problem. What happens inside of a queue is that you have some input signal or input speed, Rx and Tx, and when the Tx rate can't support the Rx rate, you start to build up packets in the queue like this. Queue has a finite length. If you exceed the queue, you drop packets. But queues here lead to what we call buffer bloat or latency. The longer the queue, the more packets, the longer the latency. So this will happen in all networks, but it is a little bit worse in LEO because of this oscillating effect, which is quite unusual. You don't really get that in any other media. So this will hurt cruise ships, airlines, anyone who's being served by a LEO satellite. And what is the fix? Well, you could imagine shaping this traffic so that you never hit 100%. You could do that. The better solve is to go from one queue to two queues. So if you have two parallel queues like this, and you split the traffic coming in to the queue intelligently, so that the longer queue here, or the more utilized queue, is used for bulky traffic, video, heavy downloads, etc. The other queue here is used for interactive, gaming traffic, web, anything that's transactional. That way, anything that suffers from bad latency doesn't get it, and everything that doesn't suffer from latency, utilization is still high. Now, how do you implement this? Well, you have to have a smart box that can identify applications in the incoming packets and direct them to these two queues, like a box from AppLogic Networks. Using AppLogic, we can look at the packets and we can identify, is this Netflix, is it Amazon Prime, or is it Call of Duty? That's how we make networks better.